So, good afternoon, everyone, and welcome to the third and last Pufendorf lecture by Frans de Waal. As you all know, Frans de Waal is a world-renowned primatologist, but he's actually more than that, and perhaps more importantly, he's one of the founding fathers of a research discipline. And this discipline bears many names: animal cognition, comparative cognition, cognitive biology, cognitive ethology, cognitive zoology. Did I forget something? Yeah. And of course, Frans de Waal's own version, evolutionary cognition. But as you all know, in Swedish, kärt barn har många namn. You can Google it if you don't speak Swedish. It is perhaps one of the youngest disciplines we have in science, animal cognition, but it's also a discipline with one of the oldest historical roots. So there are more or less no philosopher throughout the millennia who has not been thinking about what is going on in animal minds and what is the difference between animal minds and human minds, or are there any differences? Of course, all this changed with Darwin, but back then we didn't have the methodologies to study animal minds. So it was not until the late 60s or even later when this discipline started to converge, or many people converged on studying animal minds. And Frans de Waal, he's been there more or less from the inception. And today he's going to give us his view on this subject and his thoughts on it. And he asks us the question whether we are smart enough to know how smart animals are. I really hope it's a yes there, because otherwise I'm out of work. So please welcome Frans de Waal.
Well, I'm very pleased to be here again. You know, the first time I spoke was in this beautiful old building that people long for at this moment here in the department, I've heard. But now we're in a new building. And especially to be surrounded by practical philosophers and theoretical philosophers, and I'm getting the difference now slowly. I'm getting the difference, and people who work on animal cognition, and so I feel very much at home. I always dabble a little bit in philosophy, but not today. Actually, today I'm not going to talk about much philosophical topics, but more the practical topics of what we know about animal intelligence and how we know these things. And I wrote this book, Are We Smart Enough? Basically because I think in the previous century, we have completely underestimated the animal mind. We had two schools of thought, according to one, and they had two boxes in which everything needed to fit. According to one, it was all instinct. Animal behavior was instinctive. And actually, I come out of that school. There was ethology with Lawrence and Tinbergen and so on. And then the other school would say that's the other box. Everything is based on conditioning and learning, associative learning, very simple learning processes, which are basically the same for all species. So they didn't particularly care about species differences. The rat or the elephant was all the same thing, basically. And everything needed to fit in those two boxes. And if you said that I have found something that doesn't fit in those two boxes, they got very upset with you. They didn't like that, to hear that at all, because it all had to fit there. And now we fortunately live in a different time. We have a whole new generation of scientists, many of them young scientists, some of them somewhat older, but we have a whole new generation of scientists who think there's a lot of stuff outside those boxes, and to try to squeeze it all in there is a sort of hopeless enterprise, and to neglect the differences between species is actually, biologically speaking, completely wrong. And so we do need to pay attention, for example, to brain size. An elephant has a bigger brain than a rat, and so we suppose that the elephant is doing more with that brain than a rat. I will go over all sorts of species, not just the primates. And so some of it will not be my own work. I want to start with 3 examples of interesting things that animals do. Mirror self-recognition. This is Rowena, one of our chimps, who has a little hole in her head. And she's using our iPhone to inspect that hole, which is caused by a male Males do these things sometimes. And so she's looking at that. It's very coordinated. Yeah, now she also is going to groom herself a little. So, chimpanzees recognize themselves in the mirror. Your average dog is not doing this. And if you have a dog who does this, you call me. And I will probably be very skeptical about the dog. So chimps do this all the time, and if, for example, in Georgia, I often have sunglasses on. If I walk up to my chimpanzees, they use my sunglasses as mirrors, and they look inside their mouth, which is a part of your body that you feel the whole day, but you never get to see. So they want to look inside of that. And the females will turn around and look at their behind. The behind is a very important part of their body. And the males never do that. The males are interested in the females' behind, not in their own behind. This is what a monkey does. I've already mentioned several times that we make a sharp distinction between chimps and between apes and monkeys. This is what a Capuchin monkey does with a mirror. So the monkey is very interested in the mirror and is not afraid of a mirror. They always say that monkeys see a stranger in the mirror. I can assure you, this is not the behavior they would show to the stranger. So that's an incorrect assumption. But they don't recognize themselves, and they don't use it to inspect themselves the way the apes do. And so that's a big difference. That is mirror self-recognition. Second thing. This is Lisana. Lisana is a bonobo who picks up a very heavy rock and starts walking. And my postdoc, Zana Clay, starts filming right away because she knows that Lisana is going to do something with the rock. It's a bit like you see a guy walking in the street with a ladder on his neck. You know he's going to use the ladder, otherwise he's stupid to walk around like that. So you know that she's going to do something. And she walks. You will not see the whole movie because she basically walks half a kilometer. She walks 15 minutes with the rock on her back and the baby. And now she picks up a few things here. And now she goes with the rock to the only hard surface in the whole forest. They live in a forest, and that's the only hard surface they have. And she's gonna, what she has picked up in the meantime is nuts. And she's gonna use the rock to crack the nuts. Now the nut cracking by itself is not so spectacular. We've known for 50 years that the apes crack nuts with stones. But the interesting thing here is that she picked up her tool 15 minutes before she even had the nuts in her hands. And she probably knew where she was going to find those nuts. So 15 minutes before she even had the nuts in her hands, she was already collecting her tool. And that is typical. There's many observations of apes in the wild who bring tools to certain locations and then start using them, but they bring them from long distances. So there's planning involved. And planning is a very important characteristic. There's a lot of research now on what is called time travel, thinking ahead and thinking backward. And the whole notion that we used to have, that animals live in the present, and that only humans are able to think forward, is now up for grabs. And actually there's some rat studies now on time travel. And so time travel is a big topic. And it's not limited to the apes. There's all sorts of studies. Last one I want to show, of three examples, is Ayumu. Ayumu lives in Kyoto and has learned to tap numbers on a computer screen in a certain order. So he can tap them from 1 to 9 or from 9 to 1. That by itself, again, is not so spectacular because we've known that these ordering things are easy to learn, and the numbers may not mean necessarily so much for him, but he can do that. But now the trick is that the numbers disappear within a few milliseconds. So for 200 milliseconds he sees them and then they disappear and are replaced by white blocks, and he's still tapping the blocks in the right order. They always appear in the different way, so the pattern is always different. He needs to look at the numbers and memorize the order, and he does that. I think now he's going to make an error. That's the error sound. But in general, he does this all the time correctly. So when this happened, sort of interesting moment, people got very upset. There were several psychologists in the US who went into training to see if they could beat Ayumu. And they trained very hard, and they wrote a paper, and they could do it with 5 numbers, but not with 9. And Ayumu is now training on 15. And so they were very upset by this. And I don't know why people get upset by these things, because, you know, there's birds who can remember 10,000 seed locations that they hide in the fall and they find back in the spring. I cannot even remember where I parked my car sometimes. So yes, animals do wonderful things and have great memory. In this case, it's flash memory. And we don't know, Ayumu's mother cannot do this. There may be an age effect here. But anyway, at some point, the memory champion of Great Britain was flown to Kyoto with the BBC camera crew to beat Ayumu. And it was never broadcast because he lost. And I don't know why people have that sort of obsession. I found a very interesting clip on the internet, and that's why I think age may be a factor. This was a little boy who can do Rubik's Cube blindfolded. So you will see how this goes. This looks very similar to what Ayumu is doing. He looks at the cube. You will not see the whole thing. I think it takes less than 2 minutes, but he solves the problem. So that's a flash memory, and so maybe our species is capable of it, but not the old scientists in the US. It's these young guys who do that. So if we look at all the species that we study, we have to be very careful how we compare them. This is a cartoon which says for a fair selection, everybody has to take the same exam, please climb that tree. And that's probably why the chimp is laughing, because that's an easy task for the chimp. It's almost impossible to find the appropriate tests that you can apply to all species. Everyone wants to know which is the smartest species, and I really cannot answer that question. Even dogs and cats, which are both mammalian carnivores, they react so differently to all sorts of situations, as everyone knows, that you cannot test them necessarily in the same way. And so if you test for cat intelligence, it's not the same as the way you test for dog intelligence. So when we do these tests, we have to find species-appropriate testing, and that's a big challenge. And that's the thing that was often ignored in the past, I think, is that everyone is going to be tested the same way. We have to avoid the clever Hans effect, and I'll explain what that is. And we have to be cautious with negative evidence. There's far too many papers in the literature that have made a big deal about negative findings, where they tried to find something and they didn't find it. And usually the negative evidence comes in, especially if we want to stress differences between humans and animals. And so then they test a chimp in a particular way and a human in a particular way, and the human passes the test, the chimp doesn't, and they conclude, and they're very eager to conclude that only humans can do a certain thing. So here, Clever Hans. Clever Hans was a horse 100 years ago who could do arithmetic. And so you could ask him how much is 3 times 4, and he would tap his hoof 12 times. And you would ask him the square root. You could say, today is the 5th, what is next week Wednesday? And he would have the right answers always. Until a clever psychologist discovered that Hans could only answer the questions if the owner knew the answers too. So then he put a curtain between the owner and the horse, and all of a sudden the horse couldn't do anything anymore. So he was not particularly good at arithmetic, and the conclusion was that he was particularly good at reading the body language of the owner, because the owner would be staring at his hoof, and when he reached number 12, he would probably look up or shift his position, and that's what Hans was responding to. So he was actually a very clever horse, but in a totally different way than people had assumed. And he was very famous, and the clever Hans effect became sort of the weapon to kill everything that we did in animal cognition. So as soon as you found something really interesting in the animals, people would say, oh, couldn't that be a clever Hans effect? And then they could shove it aside and they could move on with their conditioning paradigm or whatever it was. So here you have the way we avoid the clever Hans effect. This is the owner of Chaser, who's testing his dog. His dog knows 1,000 words. And he's testing him, asking him for objects.
Fine, Paul. Good girl. Okay, very calm. Yeah, that's pause. Case. Find goose. Go find goose. Find goose. Yeah, that's goose. Very good. Goose. Inside. Peppermint. Find peppermint. Find peppermint.
Now the interesting part is the screen. So the screen between him and the objects makes that we avoid the clever Hans effect. Because if that screen wasn't there, everyone in science would say, well, probably the owner is looking at the objects. And that's how the dog knows. Many of these testers, other dogs who know this kind of thing, it's almost always border collies. Many of these dogs, they are tested by looking at something in a different room. So you sit in this room and you say, go get that object, and they run off to the other room and get it. And that's how we avoid the clever Hans effect. Now, this is how child studies are done.
Between the capacity to use tools, speak, and cooperate, our brains have evolved into something truly unique.
So in child studies, clever Hans effects are not avoided. Now, I've heard that children are very smart, but I'm not convinced by the studies that I see, because they're not rigorous enough by the standards of animal intelligence studies. And so I'm a biologist and I live in the psychology department and I hear all these things about developmental psychology, but I think a lot of it is exaggerated. The kids get an enormous amount of surplus information that we don't provide the animals with. Much of it is, of course, linguistic, but also children sit on the lap of their parents while they're being tested. Well, that's a source of confusion right there. So that's how children are tested. So species-appropriate testing, that's a very big issue. And I'm going to give you a few examples. One has to do with imitation and cultural learning. There was a time, believe it or not, we don't talk about that much anymore, but there was a time where people said that imitation was uniquely human. And this was based on studies in which children would sit in front of an experimenter, the experimenter would demonstrate something and the children would imitate it. An experimenter would sit in front of an ape and demonstrate certain things and the apes wouldn't do anything. And so they had concluded that apes cannot ape. We have the verb aping after all, but they cannot do that. But that was based on a very strange sort of test, because the child was tested with its own species and the chimp was tested with a different species. That must make a difference, you would think, but that was totally ignored. And so here we had a negative finding that got a lot of attention for the wrong reason, in my opinion. And so we decided with Andy Whiten and others to set up an ape-to-ape project and on chimpanzees. This is the Yorkies Primate Center where we do these studies. And so we call the apes out of the group and bring them into a testing room and we can demonstrate them something there. So this is what we call the cognition room, and that's where they are. And they come in on a voluntary basis, which is always a sort of struggle to get them in. We bribe them. We have air conditioning, which is a good one. And so they come in. And then we set up an apparatus, and the beauty of that apparatus is that you can get food out of it in two different ways. So the same machine is used for two different groups of chimps. There's two ways of getting food out of it. You can take a stick and lift something up, and the food will roll out. Or you can take the same stick and poke it in there and push very hard, and the food will roll out. So you have the poking and the lifting. Those are the two techniques, and if the chimps would sort of randomly perform or figure it out by themselves, you would expect sort of 50-50 distribution of these two techniques. Then we teach one high-ranking female in each group to do one technique or the other. So in this group, the high-ranking female has become a poker, and this one has become a lifter. They are the models. The reason we use high-ranking females is if you use a low-ranking female, then she's very easily displaced by others. So she cannot really demonstrate because they're supposedly going to demonstrate the technique to the rest of the group. And if it's a low-ranking female, they're going to get kicked away. And so you need a high-ranking female. We don't use the males because the males have no time for our experiments. The males are very busy. They are in politics and sex mainly. And if you bring in a male and you don't bring in the other males, he's going to be very upset because his buddies are, who knows what they're doing out in the group there. And so he needs to have them all in the building. And if all the males are in the building, then the building becomes a big pandemonium and we cannot really do anything. So we need to use high-ranking females for this. Then we look at what the rest does. And in this group, everyone became a poker. And in this group, almost everyone became a lifter. We actually, sort of interestingly, we had 6 individuals who did quite a bit of poking in this group. Poking apparently easier for the chimp than lifting. But they converted, most of them converted back to lifting. So we call that conformism, and there's now quite a few studies on conformism. They started doing what everybody else was doing. So that's another interesting aspect of cultural learning. We have a lot of talk about animal culture, is that you prefer, even though you know there's another technique that is equally successful and effective, you prefer the technique that everyone is following. So I'll show you a little video clip of this.
All you get is a stick. And I'm going to put in it a food reward, and it's your job to try and get that out.
Right. How about this? This looks like... I soon discovered one way to get the reward. Poke at it. I was a genius. I did it. But the machine has a second solution. It took me a while, but eventually I realised. You lift the lever.
There you go.
I was a genius again. So there you have it. 2 ways to get the M&M. Lifting and poking. The next step was to teach one chimp to poke and one to lift. Then, put these new expert chimps into different groups and see if the other chimps learn from them. Creating 2 separate cultural traditions. The lifters and the pokers. And because they're so eager to learn, it works.
Yeah, so they clearly learn from each other. So Vicky Horner has done many variations on these experiments. And we believe that chimpanzees are excellent imitators. And so that is a bit related to that puzzle of why did people not find imitation at first in the apes, and I think it had to do with the testing paradigm, where they were not supported by their parents, not sitting on the lap of their mom. They were sitting alone and with a different species, which is, I think, was the biggest issue for them. And here they're learning from each other, and that's much simpler for them. So negative evidence, you have to be careful with negative evidence, and far too much has been made of it, in my opinion. And a typical example is what happened with the elephants. The elephants were tested on mirrors, and they were found to fail the mirror test. So this is the test that Povinelli did, and the conclusion was, of course, that, which is sort of overly dramatic conclusion, that elephants have no self-awareness. So that was the conclusion, and what you have here is an elephant who is behind bars and has a relatively small mirror that is at foot level. And so the bars are multiplied by the mirror. So the elephant, what the elephant sees is 2 sets of bars and feet moving around. And the elephant had not responded very well to this particular situation. And the conclusion was that he lacked self-awareness. But I think that's very puzzling. And so we set up an experiment with Josh Plotnick on, this is Pepsi the elephant. This is me sitting on Pepsi. This is Josh marking Pepsi. And this is in Thailand that we do these studies. And Pepsi is tested on a mirror that is the size of an elephant. And so it's a very big mirror, and it's also a mirror that he can feel behind, which is very important, also for children, when you test children. You want to explore the mirror and understand what a mirror is before you get involved in it. And so Pepsi is marked with visual paint on this side of the head, And on the other side of the head, he is marked with a sham mark, we call it. It's the same paint without the color substance. So the elephant feels being marked on two sides, but only one of them is visual. And he can, of course, not see the mark without a mirror. That's the trick, the whole trick of the mirror test. So you will see how this goes. This is Pepsin, marked on the left side, in front of a big mirror. So there's a mark on the other side that you don't see. Now he's marked on the right-hand side. It's of a different day. Yeah, it's a non-toxic paint. And now look at what he does here at the very end. He looks inside his mouth, just like the apes do. So he extends from the mark test, because there's a lot of criticism sometimes of the mark test. It's a learned trick or whatever, but he extends that test now to, oh, I can also look into my mouth, and that's what he does. Yeah. So the elephant does pass the test, at least some Asian elephants, African elephants. We've tested African elephants, but they are very different. They are very destructive. They have these enormous tusks, and they like to poke in things, and so it has cost me a lot of mirrors, and I've given up on the African elephant. And it doesn't mean that they cannot do it. That's always the issue when you test different species. So you have to be careful with negative results, and this is the mantra, of course, of experimental science. Absence of evidence is not evidence of absence, and that has been forgotten far too often, especially when it comes to comparisons between animals and humans, because there's such an eagerness to find uniquely human things, and then as soon as we don't find it in a species, we say, well, we're the only ones who can pick our noses while looking at our feet or something. Now, the cognitive ripple effect, as I call it, has to do with convergent evolution. Has to do with the fact that we very often find spectacular capacities that we had not expected in other species, in the apes first, usually in chimpanzees, but usually within 5 years there's someone who works on dogs or dolphins or corvids, and other species are coming in. And then at some point the rats come in. I talked, I think in my first talk I talked about empathy. That's what happened with the empathy literature. We start with the apes, but now we are doing lots of rodent studies on empathy. And I think this happens all the time, and the example that I want to give you is tool use. And tool use is an interesting category because we are so impressed by things that we are good at. And tool use is something that we are really good at. So language and tool use are sort of the specializations of the human species. And capacities that we're not good at, we don't particularly care about. So if let's say, if I turn all the lights off here, and I release a bat and an insect, the bat can catch the insect. It's incredibly complex what the bat is doing with the echolocation. Anyone who designs a radar system for an airplane knows the correction for the flight and for the patterns, and it's an extremely complex thing. And it's a cognitively very complex task, but since we don't do it, we don't care about it. Who cares about the bat? So tool use is what we usually go for. And I think that's a human bias right there. So it all started with Wolfgang Köhler. Köhler, sort of the founder, in my opinion, of evolutionary cognition. And Köhler didn't think about the two boxes of instinct and learning. And he presented his apes with challenges. Instead of training them to do something, he presented them with problems. And so he would hang a banana high from the ceiling, and he would give the chimps a bunch of sticks and boxes, and then see what they could do. And he would describe that the chimps had all sorts of ways of trying to get there. One was to drag him to the banana and try to climb on top of him. So they had all sorts of techniques, but most of the time they couldn't. And then they would sit around, and at some point one of them would jump up and stack the boxes and take a stick and reach the banana, and he would call that a moment of insight. So as if the chimp had solved the problem in his head. So it involved thinking. Now, this is completely wrong. This was completely wrong. The behaviorists hated Köhler. I still meet people who cannot pronounce the name of Köhler. They can only say Köhler like this, because Köhler was the first one to say animals can maybe think. Now we have actually quite a few studies on insight in animals, but this was the first one, and I think it was a very important one. Now, recently at the Arnhem Zoo, I tried to replicate the Köhler experiment. So we hung a bunch of bananas very high. The chimps live on the island, and we gave them sticks and boxes to see what they would do. They didn't do exactly what Köhler said, but it came very close. This is a young male here who has picked up a box and a stick. So that's already a perfect combination that he has. And I feel he does particularly well with the box. He puts the box always in the highest possible position, which is great, I think. So he has some understanding of this. Now he's going to reach it. There he goes. And that's the alpha male. The alpha male has a different strategy. It's equally good, I think. So then we found in this little experiment, we found that a female, a high-ranking female, she had a solution that Köhler had never described and that I'd never heard of in the literature, but it was a very effective solution. You see how that goes. So she was actually the most successful, and this is not a permissible technique, I would say, but she did that. So then these same chimpanzees, they became, a couple of months after this, they became very famous because they brought down a drone. I'll show you how that goes. They have seen the drone flying around many times, and they see birds flying around all the time. The birds they don't mind, but the drone they didn't like. And so they would line up 5 of them. So that's planning right there. They were sitting 5 of them in a tree with big sticks waiting for the drone. And the zoo was very concerned that they would have to pay for the drone. The drone was from GoPro. But GoPro turned it into an advertisement. And you will see the advertisement. GoPro thought it was a great thing that the chimps did this. And so you will see how that goes. Here we're flying over the zoo with the drone. These are siamangs. Now we're reaching the chimps. There's 5 of them waiting with sticks here. So meet your chimp overlords here. So that was really successful, and what you saw here is not only tool use, but you also saw planning, waiting and planning and coordination, maybe even, who knows what was going on there. Then after the chimps came the capuchin monkeys. Now this is sort of interesting. In our field, there's all these competitions, like my dolphins are smarter than your monkeys and stuff, you know, like that's always going on. And so when the Capuchins came with the nut cracking, there were a lot of chimp experts who were unhappy about that, because the nut cracking was always considered like the summon of chimpanzee culture and tool use, because it's very coordinated and you need 2 tools. To combine 2 tools on an object is really complex. And so they had made a whole beautiful evolutionary scenario saying that chimpanzees have entered the Stone Age, or they would call it a lithic culture, just to get close to the humans, and that the whole story sort of fit beautifully together, as chimpanzees have entered the Stone Age. And there was no room for capuchin monkeys in that story. And the capuchin monkeys have tails after all, and the South American primates are very distant from us in the primate order. And so initially they tried to poo-poo what the Capuchins were doing. Like, oh yeah, sometimes maybe they find a nut and they find a few stones and they bang them together and who knows what happens with that. And so they tried to sort of diminish what the Capuchins were doing, but we now know that they bring the stones from very far and the nuts from very far, and it's a very complex task. And a Capuchin monkey is not nearly as strong as a chimp, so lifting a big rock like that is a lot of work for the Capuchins, and they're very good at it.
Palm nuts are extremely hard and difficult to crack open. It only works if you get it exactly right. Somehow, these clever monkeys get amazingly good at it.
Can have the lights a little bit down. How do we do that? So yeah, this is the Capuchin monkeys, and so the Capuchin monkeys have been tested, of course, also in captivity for a long time, but this is from the field, and so that was extra impressive. Then the corvids came. Well, you all know about the corvids, because your whole city seems full of corvids, and corvid people in addition. So you probably know all of this, but the corvids came and were also not welcome, because, you know, they were doing things that supposedly only the apes were doing. And so we have all these little competitions going on. And with the corvids, it started really with observations on the New Caledonian crows, who used tools in the wild. And that actually didn't reach a whole bunch of people at the time, but they manipulate leaves and they strip the sides of the leaf and they use the core to extract grubs from crevices. And so they actually make tools, and tool making is a big deal. There was a book in the 1950s, and the title was, by an anthropologist, the title was Man the Tool Maker. And the whole point was that what sets us apart as a species is that we're not just using tools, we're making tools. Fabrication. So then, of course, we know that the chimps do that and orangutans do that, but now we knew that for the New Caledonian crow. But since it was not in a controlled experiment, I don't think it reached a lot of people until Betty the crow did it in Oxford in a laboratory. So they had a tube with a little bucket with meat in it, and Betty was giving a straight piece of wire. And with the straight piece of wire, she couldn't do anything. So she tries to poke at it, but it doesn't help. But then she takes it out and she starts to bend it until she has a hook. And now she has a hook. And she can get the little bucket out. So that was a very important moment for Betty, as well as for science, I would say. And I think the whole picture then at that point changed, and people started testing corvids on all sorts of other tool use. There's all these fancy studies now. I cannot go into the details, but anyway, we know that corvids are quite good at this kind of tasks. Then we got other species. This is the octopus using tools, using coconut shells to hide in. I personally actually think the locomotion is more impressive than the tool use. I'm not sure I could coordinate like this. And so, yeah, we got the octopus, we got the alligator, we got certainly many bird species that use tools one way or another. And so tool use is one of those many characteristics, I would say, that has a ripple effect in the sense that we start out usually with the apes, and then we move to all sorts of other species. So I would say every cognitive capacity that we discover in other animals ends up being older and more widespread than we thought. And I think that has been going on now for the last 20, 25 years with a lot of cognitive characteristics, including theory of mind, planning, all sorts of things, is that it's usually not limited to the apes. And so this whole ape focus, even though I'm partly responsible being an ape researcher, this whole ape focus is actually wrong, I think, and we should have a much broader perspective on cognition and not even exclude the invertebrates as we usually do. We should include everything in there. And most of that is what we call convergent evolution, not when species are related, like let's say Capuchin monkeys and humans or chimpanzees and humans, they're all primates. But when they're unrelated and there's an enormous evolutionary distance between them, we call it usually convergent evolution. So a few other topics I want to mention in connection with animal intelligence. One is cooperation. We do a lot of studies on cooperation in the primates. And the whole notion that primates have trouble with cooperation or trouble with altruism, and I've talked about also the empathy studies that we do, is now sort of gone, but there used to be an enormous amount of skepticism. Can I get the lights even further down? This is a very poor quality 100-year-old movie. Yeah,
can we take it up again in a few seconds?
Huh?
Can we bring the light up again in a few minutes?
Maybe at some point, yeah.
Thank you, sir.
I always like the lights off. But this is this old movie. This shows that Robert Yerkes and his students were already 100 years ago interested in chimpanzee cognition. They give the chimps a very heavy box that one chimp could not pull in. It's called the cooperative pulling paradigm. And they bringing it in. There's food on the box, of course, otherwise they wouldn't be pulling. So now what you see is that they feed one of the two chimps. One of the two has gotten food, and so is not interested in the task anymore, has lost his motivation. Now look at what happens at the end. He takes almost everything. So there's two interesting, you can bring the lights up a little. So there's two interesting parts about this. One is that the chimp on the right has a full understanding that he needs the partner. This is often tested now in cooperation tasks. Do you actually understand that cooperation is needed for the task? So this chimp, he activates the partner, so he seems to understand that. And the second thing is that the partner is willing to work even though the partner is not interested in the food. So why would that be? Why would you work? Yeah, so it's a tit-for-tat thing. And so reciprocity is very highly developed, and these two chimps probably live together, and they do each other favors all the time, and that's how this happens. So that's the original test. There's now many studies on the cooperative pulling task, but I still think this is the most beautiful one, and this was done 100 years ago. Now, we did it recently on elephants. On elephants, the problem is that it's hard to design a box that is too heavy for one elephant. And so we did a very different thing, a single rope runs around an apparatus, and if you pull on this side of the rope, it disappears on the other side. And so the two elephants have to pick up the rope at exactly the same time. And then we make life more difficult for them by holding one back and see if they understand that they need the partner.
In Thailand, Dr. Josh Plotnick and his team have devised a unique challenge to find out, using a sliding table, some rope, and an irresistible reward. So here's the problem. The elephants need to be able to pull the table closer to gain access to the sunflower seeds, and they need the rope to do that. But if only one of them pulls the rope, then they both go hungry. Can they work together to solve a novel problem? And more importantly, do they actually understand the concept behind it? The first time the elephants are shown this task, they fail. But this is a necessary part of the learning process. And something is definitely going on in there. A 4-kilogram brain is working it out.
The first thing I think that they learn, and there has to be some learning involved, and this is a task they've never experienced before. The first thing is that they learned that their partner needs to be there. And I think in some ways they've learned not only does their partner need to be there, but their partner needs to be doing something.
It doesn't take them long to figure it out. But Josh needs to prove that their brain power allows them to understand what's going on, so he releases one elephant before the other in the hope it'll wait for its partner. This moment of waiting is key. Josh gets the answer he was looking for.
What you're seeing is that the elephants are thinking about cooperation, and that actually demonstrates how smart and how well adapted these animals are.
It's all very well proving that animals understand cooperation. But how does it help them to survive in the wild?
Now this is a very difficult task. So chimpanzees can do it, elephants can do it, but they've tested many other animals. They have also tested rooks and parrots and some other species, and they cannot do it. There's a lot of species who cannot do this, and I think that's related to the fact that it takes some emotional control. You have learned over time that if you pull at something, you get a reward, and now all of a sudden you need to suppress the response. And the elephants are capable. The elephant is a very patient animal, and I rate actually the intelligence of elephants at about the same level of that of apes in many ways. Now we started doing this cooperative pulling task on chimpanzees because we wanted to look at how they deal with competition. There was a claim in the literature that yes, animals cooperate, yes, humans cooperate, but we are the only ones when there's a competitive tendency to be able to overcome that. And we do that by punishing, or we do it by other means, but we have that capacity. And so we set up a situation with chimps where instead of just two chimps pulling at an apparatus where we choose the partnership, we did it in the open where everybody was present. So we did it in a group with 20 chimps. So everyone is present, meaning that high-ranking chimps can interfere and beat others out of the way, or low-ranking ones can be freeloading and sitting next to someone and steal their food and all of this. All this competition was possible. And we wanted to see how they would handle that, and if they would not be able to handle that, then this would end up one big bickering group of chimpanzees, and no production, so to speak, would occur. And there was some competition here. You see a female who tries to get rid of a female at the apparatus, and she starts to drag at her and pull at her. And but this is low-level competition. So for chimps, you know, chimps can bite each other and make injuries. This is nothing. Chimpanzees are very tough, and this is really very minor what's going on here. I'll show you a video of the experiment. So here is the apparatus mounted on the enclosure of the chimps themselves. We don't train them at all. We put up the apparatus and they have to figure out how it works. And they have to look at each other. That's why they're looking at each other. They cannot do the task unless they pull at exactly the same moment. Now you have 3 of them. Sometimes we do 3, and that's a bit more difficult, but they can still do that. So they have to coordinate and pull in at the same moment, and they get the food. So that's typical. They did this many times. Now here you have a small competition. The alpha female walks away. A young female moves in and starts to pull. And as soon as she gets food, the alpha female tries to steal it from her. So that's a little competition. There's all this stuff going on. This is a female who tries to get rid of a male. She's not dominant over the male, but she knows how to move him. So that's mild competition. And then we got these very coordinated things going on. This is two females who come from a long distance. They walk towards the apparatus, and sometimes there are three. Sometimes they go get somebody and bring them to the apparatus. And so there's all these coordinations going on, and we don't know exactly how they communicate that they are planning to work together at the apparatus, but it was all very highly developed. And then when we looked at the data, this is what we found. We have an index that runs from +1 to -1. +1 means that in a session, each one is sessions here, that in a session all the interactions are positive and cooperative. -1 means that all of them are negative and competitive. And 0, of course, is when there's a sort of balance between the two. And as you see, they start out with quite a bit of cooperation, and then it breaks down. And what happens here is that more and more chimps learn how this thing works, because we don't train them, so they have to learn that gradually. More and more of them got involved, and the more of them got involved, the more competitive the situation was. And if we had stopped here, you would have concluded that they're not particularly good at solving this problem, but this is what happened when we went to 100 sessions, and as you see, they become extremely cooperative. Basically, 5 of every 6 interactions is cooperative. And so they reach the same level that John Gottman proposed for human organizations. He said in human organizations, you never have perfect cooperation. You always have some conflict going on. And that's the ratio that he found. Actually, John Gottman started with marital relationships. So if you're married and you have this ratio, 5-to-1, positive versus negative interactions, you're probably okay. If you have a 1-to-1 ratio, you probably want to see a counselor. That's probably not so great what's going on. So this is the balance that John Gottman proposed, and that's exactly what our chimpanzees seem to achieve. And so we have no reason, given that we had almost 4,000 cooperative pulls, they were basically non-stop pulling these chimpanzees on the apparatus. We have no reason to propose that they have trouble dealing with competition. And the way in which they do this is sort of interesting. There's 2 things that they can do. One is partner choice, and it's the most important one. You only cooperate with those who you like and those who are good at cooperating and don't try to cheat on you, and you avoid those individuals who don't. And individuals who are too competitive, they learn very quickly that the others are avoiding them. They don't want to stay with them or work with them. And so they learn over time that they have to become more cooperative. And that's why this graph went up. The second thing that they do is punishment. They either punish directly if someone tries to steal from them or tries to freeload. They may punish directly, but also there's third-party punishment. There's outsiders who come in and step in and punish the one who's doing the freeloading. And so that's very similar to the human data. And so the chimpanzees are really good at this. It was always a puzzle to me why people claimed actually that the chimps were not so good at this, because in the wild, they do a lot of cooperation. Chimpanzees have coalitions, they defend their territory together, they hunt together, there's all sorts of stuff going on. The females do babysitting for each other. There's an enormous amount of cooperation going on, and so there was no reason to not expect this. All right, now I'm going to get to a few topics that I've already treated in the, and I'm going to present them slightly differently, but for those of you who attended the first 2 lectures, there will be some overlap, inevitably, with what we do here. I do a lot of studies on empathy, and I got involved in that long ago, and actually it started with my studies as a graduate student, where I discovered that not only do chimps reconcile after fights, but they also console individuals after when they're distressed. And so I got very interested in this. This is a dictionary definition of empathy, the ability to understand and share the feelings of another. And you see the 2 components of it. You see the understanding part, which is the cognitive part, and the feeling part, which is the emotional side of empathy. And empathy has basically these 2 channels. One is the body channel, where you are in synchrony with others. There's mimicry of the facial expressions of others going on. There's emotional contagion. You're affected by the emotions of others. And all of this is initially, at least, through the body. And so it's a bodily process. that starts very early in life. So it starts on day 1 of life when babies cry, when they hear other babies cry, and it goes from there. And it's probably this part of empathy is not uniquely human. We know of a lot of animals of bodily mimicry and emotional contagion. Then the second part is perspective taking, where you take the perspective of somebody else and so try to understand the situation. So you're not only affected by the emotions, you want to know where they come from and what the situation is of the other. Now we study the body synchronization by looking at yawn contagion. So we do these studies. Yawning is of course present in all the vertebrates. This is a yawning gorilla. And so we show our chimps yawn videos. Here there's a chimp looking at an iPod with yawning chimps. And this is a very simple test to get at the synchronization part. It's not exactly what I would call empathy. There's not much of an emotional component, I think, involved in this. But we did this, and what we found is that the chimps are most sensitive to the in-group. This is what we find in basically all the empathy studies. You're more sensitive to individuals who are familiar and similar. And so the in-group are videos of chimps that they know, and the out-group are videos of chimps that they've never seen, and they only do it for the chimps that they know. And this has been found in the mouse studies now, in the rat studies, in the human studies. There's a human study that was done in Italy where they looked at yawning people in train stations and waiting rooms. And you stand next to a stranger who yawns, you're going to be unaffected. You stand next to your wife who yawns, and you're going to be yawning. And so yawn contagion follows the rules, basically, of empathy in that it's biased, it's socially biased. Now, to get closer to what we normally talk about when we talk about empathy, is consolation behavior. So this is work that Zana Clay does at Lolaya Bonobo Sanctuary. This is a bonobo who embraces one who has been just in a fight, has just lost a fight, and that is typical consolation behavior. I'll show you a video of a consolation. So here you see a baby bonobo of maybe 3-4 years old who gets bitten by this female and screams, and you will see how this goes.
Brandon, you just attacked Malak.
So that's very effective and very quick, and it's a very typical behavior of the apes. It happens in the apes all the time. In monkeys it happens much less, but in the apes this is a very typical behavior, consolation behavior. And it's actually the original type. When the original studies on empathy started on children, was also consolation behavior. So the original studies on children was you would ask a family member to cry, and then you would see how the children responded to a crying person. And so that's also consolation behavior. And so now there are many studies on consolation, not just on the primates. This is sort of the ripple effect here. There's consolation studies in all sorts of species. Now in the bonobos, it's sort of sad that the sanctuary exists because these are all traumatized orphans. So what we have in Africa is a lot of bushmeat hunting, and the bonobos are shot or killed by poachers, and the poachers, they bring the meat to the market, but the baby bonobos they keep alive because they are worth more alive than dead. And they are then often confiscated and brought to the sanctuary where they are raised by humans and released. And so these are all traumatized orphans, except for a few babies on the backs here of these females. So there's a few bonobos that are born in there. It's a very interesting group, the traumatized orphans, because in human orphanages, Romanian orphanages, there's a lot of studies on those. And basically what has been found is that they are emotionally disturbed. They don't have, of course, firm attachments. They are emotionally disturbed. They're not good at self-regulation of emotions, which I think is essential for empathy. And so they have a lot of trouble with empathy. And that's basically what we're looking at, the traumatized orphans in the bonobos. And when we test for this, we look at, for example, the rate of consolation behavior by juvenile bonobos, adolescent and adults, and you see it goes down. And so basically what happens is that with development, the bonobos become more and more selective in who they... It doesn't mean that they become less empathic, but they don't show their empathy equally to everybody the way they do when they're very young. But the biggest difference is this group. We have only juveniles for this, the mother-reared ones. And as you see, they do far more. At the moment, we're doing a follow-up study. Actually, it's now 5 or 6 years later on these guys. And they do far more than everybody else. And so it does indicate that, as in humans, being a traumatized orphan is not good for your expressions of empathy, as we would expect. Now, then we found consolation in elephants, and as I said, it has been studied in dogs, and it has been studied in all sorts of species. And I do want to show about elephants this little video clip of targeted helping. I've spoken about that a while ago, about do you, and this gets more to the cognitive part of empathy, do you understand the specific situation of somebody else? That takes perspective taking, and this is a sort of interesting clip in this regard. This is a young elephant who has been trying to get out of this ditch for hours and has been unsuccessful and starts to panic. And you will see an adult solve the problem. This is in Indonesia. So this is very interesting stuff, because this requires understanding what the problem is with the other. The young one is vocalizing, so there's a response to that. But it also requires that you understand what exactly the problem is and how that problem should be solved. And targeted helping is one of these expressions of perspective taking that we see in some large brain species, such as dolphins and apes and elephants. It's actually quite a common situation. Now, recently we were able to do some neuroscience on empathy, which we had been unable to do with the apes and with the elephants and with all the other animals that we worked with. And I'm not going to give you the details, but we did this on prairie voles and brought them in a situation where they could respond to a distressed individual, and we found that they console them. And basically the support for the empathy hypothesis is that, first of all, we find the same social bias that we find in all the empathy studies, is that they only console mates and siblings. We find emotional contagion is physiologically you can measure, and there's a perfect match between the two partners, the male and the female. If the female is very stressed, the male is very stressed, even though the male was not involved in anything. It was the female who was involved in some things. So there's a perfect matching between their stress levels, which is emotional contagion, and also if you block the oxytocin receptors, the behavior disappears, and so oxytocin is involved. And the conclusion from this particular Waal study that we published last year is that the neurobiology of empathy in the rodent is probably very much the same as the neurobiology of empathy in humans. And even though the rodents probably don't have this perspective-taking part, at least not as developed as in some larger brain species, they have the basic empathy mechanism going on. Now, the last thing I want to treat, and this is another thing that I think I treated in the second lecture, is a brief clip about fairness and unfairness. Now, nature is very unfair in many different ways, but not necessarily between members of the same species. And so when members of the same species are cooperative, like these two lions who together have a pride and a territory, you need to watch how things are distributed. If these two males, they're probably brothers, but let's say they're not brothers. If these two males work together, they need to divide who mates with the females. They need to divide who gets meat, who's going to fight with the neighbors, or how much risk are you willing to take. There's all sorts of decisions that need to be made for this to be a successful cooperation between those two males. And if the benefits for the one disappear and the other one keeps all the benefits for himself, there's a problem in the cooperation. They cannot be sustained. So you do need to have some sort of way of solving that issue of fairness. So a cooperation requires benefits for all, one way or another, and that requires some degree of fairness. And so we set up these experiments with Capuchin monkeys, with Sarah Brosnan, where we tested this out, where we had two Capuchin monkeys side by side, and they could do a very simple task, and they would either get both cucumber or they would get both grapes. But of course, if one of them gets grapes, which are 10 times better than cucumber, and the other one gets cucumber, you create inequity. And that's what we did with them. And what we found is that if you give both cucumber, they do the task all the time. If the partner gets grapes, they do the task only half the time, so they lose interest in the task, even though they get the same reward as before, but now the other guy is getting grapes. And if the grapes are given to the partner doesn't even need to work for the grape, they really don't want to do it anymore. So they're very sensitive to this situation, and I'll show you a little video of it. And this video has now been seen 100 million times, I've calculated, on the internet. And many of you have seen this one before or have seen it the last lecture, but I always hear from people they can't get enough of it, and I think many people click on it many times. So here we go. The one on the left is the cucumber worker, and the one on the right is the wealthy 1%, so to speak, who works for grapes. Gives us a rock, that's the task, and gets cucumber, and eats the first piece. The first piece is still perfectly fine. Gives us a rock and gets a grape. The one on the left inspects that. Gives us a rock and gets cucumber. More cucumber. So you see the body language. The reason you're reacting to it is that the body language is very much that of a primate. You know, we have the same body language, of course, and it's a very emotional reaction. Let me say a few things about this. When we published this first, this was in 2003, in Nature. We got all sorts of reactions, positive reactions, negative reactions. One of the negative reactions, I've already mentioned one of a philosopher who said it was impossible that they had this, but there was another one who said, who wrote us angrily that we must be communists because we believed in fairness. And I think my monkeys are extremely capitalistic. I think to compare your income with your neighbor is a very capitalist thing, and I think they're capitalists, basically. So there was some criticism of the experiment in the sense that they would say, well, maybe this monkey is not upset because the other one gets grapes, but because there are grapes available and he's not getting them. So that's the alternative explanation. And we ruled that out. We did a bunch of experiments where, actually one of the experiments was sort of mean, where we would have 2 pieces of cucumber to give to the monkeys, but before we would give them, we would wave grapes in front of them and then put them away. So they knew clearly that there were grapes available, but they still ate the cucumber. So it's really the fact that the grape goes to the neighbor. That's the issue. And it's a sort of resentment. It's an emotional issue. That's why the reaction is so emotional. And at the moment, I'm writing a book about animal emotions because I think a lot of these things are not just cognitive. We're just not looking at cognition. We're looking at cognition and emotion. The 2 things are almost impossible to separate. So we published this paper in 2003. And there was all sorts of discussion, and people started repeating it. And there's now studies on corvids and dogs and some other species, and monkeys for sure, and chimpanzees. But it's only when 10 years later we made this video clip that no one doubted it anymore. This is interesting for the scientists here. So you can produce a paper in which you have, let's say, I don't know how many we had, a dozen or more subjects. And you have a statistical test, and you do a lot of data collection, enormous amount of data collection, and you prove your point in that paper statistically. But a little video clip of 1 minute, in which the emotional reaction is shown, is more convincing than all the statistics, in my opinion. That's what happened in this particular case. And we did this video. We decided to use monkeys who had never done the task before. We thought maybe they're getting blasé, maybe they've seen this so many times that they don't react anymore. Let's take a few monkeys who've never done it, and that's how we got this very strong reaction. So then we have all these mothers who do my monkey experiment on their children, and in a way that I would never get permission for at the university. And you will see how this goes. This is a boy who gets a whole cookie, and the girl gets a half cookie.
You want cookies? Daniel, here's one cookie. Anna, this one's for you. Come on. Really?
So she reacts basically in the same way as the monkeys. My feeling is that if related species like capuchin monkeys and humans react in similar ways to similar circumstances, you have to come up with the same explanation for the two. So I don't believe any of this nonsense about you shouldn't be anthropomorphic and stuff like that. It is evolutionarily much more elegant to come up with the same explanation for related species than different explanations or different terminology. So that's how I look at this. Even though in this particular case I should add that I think the girl is very unreasonable. The girl is half the size of the boy, so half a cookie seems perfectly fine to me. I recently met a woman who has at home a Great Dane and a Chihuahua, and she says that the Chihuahua insists on the same amount of food. And that's a very unreasonable position to take, I would say. So I want to summarize. This is a quote from a physicist. What we observe in nature is not nature in itself, but nature exposed to our method of questioning. And that's exactly what has been going on in my field. Is because of the impoverished theoretical paradigm of the behaviorists who wanted to reduce everything to conditioning, we were asking, in my opinion, the wrong questions. We were asking questions that related to conditioning. Well, and then, of course, you confirm that that's the main thing to do. But fortunately, we are now living in a time where we ask many more interesting questions, and we have sort of dropped that whole perspective, at least the younger generation of scientists has. And so we're getting much more interesting answers also because we are asking more interesting questions. This is Darwin, who already long ago said the difference in mind between man and the higher animals, great as it is, certainly is one of degree and not of kind. And I think most of us would now agree with that position, even though that was contested. And there were, I think it was in 2005 or something, there was an essay in Nature saying that Darwin was actually completely wrong on this issue. And this is my own conclusion. There are many different cognitions, I think, in the animal kingdom. Cognition varies enormously by species and by situation. And I look at human cognition as a variety of animal cognition. And I thank all the people who work with me and do these experiments, and I thank you for your attention.
So, questions?
Hey, thanks for your great talk. I had two questions. One was...
Do one at a time.
Okay. First of all, with the monkey experiment on fairness, how did the monkeys react after they got back together in their cages? Did they keep the resentment against each other?
No, we give them an enormous handfuls of goodies at the end of the experiment. So they have forgotten by that time what happened, I think. So we've never seen, we followed them up because they live in a group. We followed them up and we've never seen any consequences of the experiment.
All right. And the second question was, how does brain size somehow play into, I guess, abilities of intelligence? If a monkey can be as smart as an elephant.
Yeah, I'm not sure that a monkey can be as smart as an elephant, but I think the brain size issue has often been sort of exaggerated. So we know, for example, for insects, very interesting. There's very interesting studies on jumping spiders, for example, who can solve the detour problem. They have very tiny brains, and so I'm not sure that brain size is as critical and as important as people say. But we usually still look at that. Now, there was, as an interesting aside, there was a paper 5 years ago which claimed that we should ignore the brain size issue. And we should not even look at body size and brain size, and we should just look at the number of neurons in the brain and just count the number of neurons. And everything was fine with that position because humans have the most neurons until they discovered that the elephant, who has a 4-kilogram brain, has actually 3 times more neurons than we do. At that moment, everyone started to panic and they didn't know what to do with the neuron count anymore. So the goal remains always to have humans on top of everything. And I'm not sure that brain size, because brain size also, we know, for example, that the birds, the corvids that Matthias worked with, for example, they have a very high neuron density. So for a bird, the brain needs to be lightweight, it needs to be. And whereas for a whale, who swims in the ocean, it can be as big as you. So a pilot whale has an 8-kilogram brain. It can be as big as they want. And who cares how big that is? So the constraints are very different by species. And a bird probably can do more with that size brain than a mammal would do with that size brain. So it's very hard to compare these brain size issues.
You haven't mentioned language at all. Are we smart enough to know whether animals have language?
Yeah, language is the one capacity where I make a difference. So if you ask me what sets humans apart, I would say it's symbolic language. Because I don't see, I see many elements of language in other species. So for example, honeybees can communicate about distant food sources and stuff like that. So I see many parts of it, but the whole thing, I don't think we have evidence for that in other species. And so symbolic communication that is as flexible as human language, I don't think we have in other animals. That doesn't mean that they may not have something equivalent that is maybe equally complex. So for example, the dolphins, which use all these click sounds underwater that we never hear unless we have a hydrophone in the water, they may have a very complex system that we don't understand. There's often a sort of incapacity for us to figure out what is going on with them. And so I wouldn't exclude that they have something that functions in an equivalent way, but I don't think it's a symbolic communication the way we do.
Hi, thanks so much. So in...
Where are you?
Right here.
Oh, okay.
Hi. So I have 2 questions. First, so far, have we only observed successful self-recognition in the big-brained species?
It has been observed in dolphins, the great apes, magpies, elephants. I think that's it. And humans, of course.
Mm-hmm. So then, does the self-recognition have anything to do with how social the animal is?
I don't know. There's all these challenges to this mirror test all the time. So there's now a new paper out on monkeys, rhesus monkeys, where they train them. But it took an enormous amount of training to train them to get to recognize themselves in the mirror. And they used a training in which there was some physical sensation involved. It was not just a visual thing, it was a physical. And physical sensation adds things to it. And I wouldn't exclude that monkeys have this kind of self-awareness, because I don't know if you know of the other paradigms. One thing that people do is they give them a computer screen on which there are two cursors that move. One is under their own control. They can control with a joystick the cursor. The other one is moving independently. And the monkeys make a very sharp distinction. So that's a self-contingency test. They make that distinction, which requires some degree of self-awareness. With elephants, recently George did an experiment, it was just published, where the elephant would stand on a platform and pick up a stick and give it to the experimenter and get food for it. And then what they did is they attached the stick to the platform, so now he would step on the platform and he could not give the stick anymore. And he would have to step off the platform in order to do it, and that's what the elephants did. So they had a sort of awareness of their own body, and this can be tested on many different species. So I'm not excluding that there is some degree of self-awareness. I'm not so absolute as Gordon Gallup, who discovered the mirror test and says you either have self-awareness and you recognize yourself in the mirror, or you don't and you don't. I think there's a lot of gradations between them. And also the people who work on children, they say that in general, children who start to recognize themselves at 18 months or something, before that time, there's already many indications, a bit like with the Capuchin monkey, that they understand something about the mirror. They don't necessarily use it to inspect themselves, but they have some understanding. Yeah.
Okay. I wonder about complexity in the environment, because you speak about evolutionary cognition. And all animals has evolved in an environment not really civilized. I mean, we have 200-300 years of industrial revolution and so on. So is it that human had become stupid, and she was much clever like 500 years ago or something, in the level of the animals, and now she's trying to measure herself and compare with them, but they still live in the wild. So they actually use their brain in what it was evolved for, but we don't. So like biodiversity, if you compare biodiversity of today, it's like, I don't know, 20 out of 100. And if you have biodiversity 500 years ago, it's more. And that biodiversity, wherever you are, that is the complexity of the environment. So if you're hunting species, you have a lot of species around you. But today you might just have a few species around you. Yeah. Thus, it's a difference of behavior. You have to behave different, because you don't have the same complexity in the environment.
You think a city is not very complex?
If you're a hunting animal, you don't have like 10 different species to compete with. You just have humans.
And you think the animals in the wild have now less biodiversity, so they don't need all that intelligence anymore? Or?
Yeah, in one way. And their environment is less complex.
I'm not sure it's less complex. They have to deal with humans, for example. Humans are encroaching in all their environments, and they're hunting them, and they build roads, and they log the forest, and that creates an enormous disturbance, and they have to deal with that. So I'm not sure it's a simpler situation at the moment, except for the few who live maybe in reserves where there's no disturbance, but in all of them there's disturbance nowadays. So I'm not sure that situation has become simpler. And also for us humans, I'm not sure that our situation has become simpler over time. I think our urban environments are very complex.
I was wondering one thing about what you meant of symbolic language. They cannot really, like, you don't know if they can put symbols over an object, for example, like to make the connection. But I remember an experiment, I'm not sure if I'm wrong, in which gorilla could see an object, and then there was another like display with different shapes, and it could relate the object with the particular shape.
Oh, yeah.
So they can actually, I mean, I don't know if there is some bias.
There's many studies of language apes, so to speak. And there's, of course, the famous Alex the parrot also who does that. So many animals can connect symbols with objects in the environment. So they do it often with sign language, and so they use sign language. Many of these studies were popular in the 60s and 70s, and people were extremely impressed by them, and they were very important studies to open the door to animal cognition, because initially people wanted talking animals, basically. That's what they wanted. In order to be convinced that animals were intelligent, they would need to be able to talk to us, which was, I think, a misconception, a very anthropocentric way of looking at the animals. But the apes did that to some degree. But then we saw the limitations of what they did also. So their expressions were usually 3 symbols long, not 20. Or so they would say, give me a banana, or let's go walk. And it was always sort of action or food oriented. The scientists had hoped to have long philosophical conversations with the chimps, but it was more like, what can we eat and what can we do? And so they were disappointed by that, and they started to poo-poo it and explain. It's sort of interesting how the history of that field is, because initially the linguists, I don't know how many linguists there are in the room, initially they had defined language as symbolic communication. When the apes learned to do symbolic communication, they said, no, it's actually syntax that is the crucial element, and that's what they nowadays say. Syntax is the core of language, because they couldn't handle the apes doing the symbol business. So then the apes were not good at syntax, that's for sure. They did not make complex sentences, and there was not much in there. And now that whole field is sort of watering down and disappearing. So we don't have these language apes so much anymore. We have Alex the parrot, who was also very influential and very remarkable, not so much because of the language abilities, but because we could use language to ask him questions. That was really useful. So you can ask Alex, you present him with a tray with, for example, 5 blue objects and 1 green object, and you say, what is different? And he says green. Or you can say, how many blue? And he says 5. It's just incredible, the sort of things that Alex the parrot was doing. And that opened the door to a lot of animal cognition studies, not because of the language connection, but we were able to use language to get a little bit at our mind.
Hi, thanks for the talk. I had a question of if you had any information on cross-species empathy, if there's been experiments done in the like thinking about humans who have pets and kind of feel for their dog or their cat. Do animals do something like that as well?
Yeah, there are some indications from the field. So there's a recent report was humpback whales helping seals against killer whales and things like that. So there's some reports from the field. No one is doing really experiments on this, and I think that's related to the fact that that we think that empathy evolved within the species for its own purposes within the species, and so this would be a sort of aberrant context in which it happens. But for example, the yawning studies have been done with dogs and humans, and so there are yawning studies where a human sits in front of a dog and yawns, and then see if the dogs want, and the dogs do yawn. And actually dogs will even yawn to just the sound of, they can play the sound to the ear. The sound of the owner yawning induces yawning in the dog. So yes, there is cross-species research a little bit, but in general, we focus on within species things.
One last question.
Hey, wonderful talk. So I was wondering, do you have any prime candidates for higher cognition in species beyond those that you have presented today? Like, do you have a hunch or two that you could share with us?
Well, the octopus is really awfully interesting, I think. So the octopus has a large brain. It's not a very social animal, so I'm mostly interested in social cognition, and so it's not the best animal for that. But octopus has these very remarkable camouflage that they do. They can blend in with their environment and color the way the environment is, and they even sometimes blend in with behavior. So there's reports of an octopus who needs to cross the ocean floor from here to there, but there's all sorts of predators around. The octopus is eaten by almost anything around. And so they will act like a plant. They stand up and they color like a plant, and they start to wave like this, and they move with the water flow, and so slowly that you would think that there's a standing plant, but it's actually a moving plant. And then he reaches the other side. So there's reports of that, and the octopus is really smart in that regard. There's also the mimic octopus, which not only mimics the coloring of a certain fish, but will swim like that fish, or will swim like a sea snake or something like that. So the octopus is truly remarkable. In the invertebrates, I already mentioned the jumping spider, I think is truly remarkable. There's a lot of research now coming up on that species. That's the invertebrates. Now, for the vertebrates, I think people have underestimated fish, for example, for the longest time. And I think if you look at the work of Bessari, Redowan Bessari, you will see that fish can be very complex and can solve some of these cooperation tasks that we do on the apes can be done on fish, for example.
So thank you very much, but please stay because it's award time.
Okay.
Yep, this might seem as something human and symbolic and weird, but it's just a regular primate token exchange. Hopefully you will see it more as a grape than a cucumber. So on behalf of the Department of Philosophy, I would like to give you this medal.
Thank you.
It's a token of gratitude for your 3 talks and for all your work and the driving force you have been. And here's also a diploma.
Thank you.
Thank you.
Well, thank you all for your attention. Yeah.